Hi, welcome to Real Learning Center. So we're continuing with our discussion on oscillations and waves. So we have completed the basics of spring and pendulum. Basically, we talked about oscillations. What is an oscillation? What is a vibration? These are things we talked about. Now we move on to wave basics, where we understand what is a wave. Okay. So let's start with a basic understanding of what a wave is. So let's start with a simple demonstration of a bullet coming out of gun. So we call it as what? We call it as movement of matter. Bullet is matter and it has moved from left to right. So it's called movement of matter. So now let's understand another scenario. So take a look at this. Here what is happening is that there are small beads. They are connected using a thread and they are going up and down. So you can carefully watch here actually. Every one of those beads are only going up and down. They are not actually moving from left to right. But something is moving from left to right. So what is moving from left to right? That is the question. So this is movement of so-called disturbance. So what is the disturbance? Each bead, instead of simply sitting, we have disturbed it. So that disturbance actually is going from left to right. The beads are not moving. The disturbance is. So movement of a disturbance is basically called as wave. Of something, disturbance of something. So we will gradually understand it in a more generalized form. So the disturbance of something basically moves in space is basically called as a wave. So that is the difference between a wave and matter. Okay. Let's understand there are two kinds of waves. Now here you can see that there is something going up. Each particle actually is going up and down, up and down, up and down. But you can see that the whole of the wave, in the sense that the disturbance itself is moving from left to right. It is like a long rope. If you do one side like this, the whole disturbance moves to the other side. So there is a disturbance that starts from this side and moves to the other. So we will say that movement of disturbance is actually, if the disturbance actually moves, the disturbance happens, displacement happens in this direction, and the wave propagation happens in this direction, left to right. So we call this basically as a transverse, where these two are perpendicular. So every particle actually goes up and down, whereas the whole wave goes from left to right. Now, if you see the next one, it is not like this. Here, every particle, if you carefully watch, is only moving left and right, left and right. Every particle, just watch any particle. None of them are actually, if you carefully watch, no particle is actually moving from left to right, from end to end. All of them are just moving left and right. And the disturbance itself, as a wave, is also propagating from left to right. So they are along the same direction. So the displacement of the particle and movement of the wave, both of them are in the same direction. So such a thing is called as a longitudinal wave. We have transverse waves and we have longitudinal. There are examples of all, both kinds of waves, transverse waves and longitudinal waves. So if you actually watch, what is a disturbance? You ask a question, what is a disturbance? So let us say the water is standstill. There is absolutely nothing happening on that, still water. So that is called as an equilibrium state. So just standing. So what happens is, if you just drop one small pebble into the water, so suddenly what happens? It creates a small disturbance in the water at the point at which you actually put the pebble. But soon the disturbance spreads, radiates, circles to the other side, all sides. And that kind of spreading, you can see, it gets created at one point, and disturbance goes up and down at that point. And finally, the same disturbance actually spreads by basically making the particles of the medium vibrate one after the other. So such a thing is actually a wave. So wave requires a disturbance. if there is no source of disturbance, then wave will not get created and will not get propagated. So if you hit something, till now it is basically having a complete equilibrium state. The moment you hit it, the bell actually suddenly starts vibrating. The moment bell starts vibrating, that vibration gives some kind of a vibration of air molecules, and those molecules will make the other molecules vibrate. So like that the wave propagates. It's a sound wave there, and it comes to your ears, and it will make your eardrum vibrate. So the wave, the sound wave, has moved from there, but all of it is because of the cause. If without vibration, there is no wave. Okay, so vibration is the root cause of any kind of a wave. Vibration means change in certain parameters. Okay, now vibration always propagates in the elastic medium. What is this elastic medium? So in an elastic medium, always if you hit something, it hits you back, in the sense that it tries to restore to the original position. So the molecule goes there and it comes back. So it actually does not go and stay there. So elastic medium always behaves in a way, it's like elastic. Okay. If you try to change the length of a rubber band, it wants to come back. So like that, if the medium is elastic, if you want to basically, there are certain mediums which are not elastic, very less elastic, where propagation is not very good. For example, in the air is less elastic when compared to, let us say, iron. Okay. So that is why in iron you can make sound propagate faster than air. Okay. So in a vibration propagates as elastic, and you can see the vibration again here is a tuning fork. When it vibrates the air and vibration propagates. Now, these are called as mechanical waves. The reason these are called mechanical waves is because there is a mechanical, physical movement of the particles. When the particles move physically, it's called mechanical waves. But the question is, are there any other kinds of waves? Particles have to move, isn't it? So there are other kinds of waves. Okay. So before going there, just an example is a sound wave. Sound wave, I said, is a mechanical. So now other kinds of waves, one of the most interesting kind of wave is actually electromagnetic wave. And in common word, we call it as light. Yeah, light actually is a wave. But is there a particle in the medium that will vibrate? So if you think so, then that means that there has to be some medium for a wave to travel. If light is a wave and it needs a particle to vibrate, then light cannot come from sun to us, so because there is a vacuum in it. So what happens here? Here actually it doesn't require a medium, because particles don't vibrate. There is no mechanical. It's not a mechanical. What vibrates is very interesting. It is not a displacement of position of some particle in the medium. It is actually the value of electric and magnetic, because light is an electromagnetic, which means there are electric fields and magnetic. You can see that's shown there like this are electric and magnetic fields. Perpendicular vibrations are happening between them. So electric field increases and decreases, magnetic field increases and decreases, and it propagates. That is basically called a light or electromagnetic wave. So there is a disturbance, but disturbance in not a mechanical kind, but the value of certain parameters, certain field, electric field and magnetic field is very oscillating and propagating. Such a wave is called as an electromagnetic wave. This is not a mechanical wave. Light is an electromagnetic wave. It's not a mechanical wave. So similarly, there are even other kinds of waves which are even more peculiar. So for example, there is something called as a matter wave. Every matter is considered a wave of something. Okay, basically wave of some probability density. It's a number. It's just a mathematical value which is fluctuating. Okay, and that thing is also called a wave. It's called a matter wave. A scientist called as de Broglie talked about how every matter can be considered as a wave. So this discussion is not for now. It's just for you to understand that there can be other kinds. So now let's go to the basics of waves. like in oscillations we figured out basically time period and frequency. Here also we can see some of the most important points. So now look at this amplitude. Amplitude is nothing but a peak difference. So each one of them actually going to differ. What is the peak difference? So look at from the center equilibrium point to the top, that arrow that you can see is the peak. So that is called as amplitude. We call it as peak. And what is wavelength? Wavelength is nothing but distance between peaks and or troughs, between two different peaks, consecutive peaks, or two different troughs are basically called wave. It is clearly mentioned in the picture here. What is the wave? Length of the wave. That is wave. It is measured in meters. Okay. And then you have one more parameter called, let's understand what is the time period of the wave. Okay, let us consider one single particle, one bead. And I am actually putting a line here to show what bead to watch. If you carefully watch this bead, it is just going up and coming down, going up and down, going up and down. And what I am going to do is I am going to take a stopwatch and find out how often it goes and comes down. What is the time period? Once it goes and coming, once for going up and coming down, between these values, let us say I will consider these two values as peak values. You see, it's going between those. If you carefully watch, then I will actually measure the time that it takes to go up and down. One time. So that time period we call it as time period of the wave. Time taken by any one point to complete one full cycle. In fact, if you see actually, the points which I have mentioned here is not even making a peak amplitude, not going till the end. Whereas there may be other points which are having a peak amplitude. But all the points, if you take any point, for example, you can take a point here and measure its time period. Even that would be same as the other one. Time period of every particle to complete one cycle, whether it is the full space it takes or not, still is same. Okay. Now, that is basically the time period of one of the particles. Okay. And that is, we call it as time period of the wave itself. And then we have wave speed. What is the speed of the wave? Speed of the wave is nothing but how fast the wave is moving from left to right. So how do you measure? Generally you measure speed by distance traveled by time. In this case, distance traveled is one wavelength. Your time is one time. So we can say wavelength actually is denoted by some strange symbol like this called lambda. It's pronounced as lambda. L-A-M-B-D-A, lambda. So wavelength is nothing but lambda. Lambda divided by time period t is nothing but the wave speed. And we also have figured out in the previous oscillations class that time period and frequency are reciprocal to each other, and how often it vibrates is frequency. Hence, wave speed is nothing but frequency into the wavelength. Frequency into wavelength is nothing but wave speed. These are some of the basics of wave. So just to get a slightly better understanding of waves, we have to understand that wave is nothing but it's a displacement. Every particle in the wave will displace from its neutral position, equilibrium position. And that displacement is a function of both space and time. What does it mean? It means you look at the wave here. So what I'm going to do is basically, I will take a photograph of this, a snapshot, just stop some point. Okay, how does it look like? It looks like one single wave like this, not moving, nothing. Okay. So what is this? This is actually, to see, you can, every point is actually displaced with respect to the neutral, some displacement, different displacement each point with respect to a equilibrium. So we call that displacement as y of x. Yeah, that means as a position, as a function of x. X is nothing but x-axis, the space. as a position of x, as a function of x, how much the displacement vary. So that if you plot, it looks like this because it is just a snapshot of this. Okay. And you can do one more thing. Now here we are clearly seeing that displacement is a function of x. X is a space coordinate. X is in space. Now one more thing that can happen. You actually take, instead of taking one point in time. So this is actually a snapshot. It is actually one point in time. At one point in time, we are seeing all the space. So can we take at one point in time, this is one point in time, all space. So we can take one point in space all that time. How do I do that? I actually take one position like this. Yeah. One point in space. And I will look at the bead all the time. As the time passes, what is happening? So you can clearly see that the bead actually is around the equilibrium position, going up and down, going up and down. Okay, so that is what is happening. Slowly going up, coming down, going up. In time, it is happening. So you can actually plot a graph of y of t, the displacement, with respect to time of that point, with respect to time. Y of t, y in this direction and t in this direction. That plot. How does it look like? It also looks like a wavelet. This is called a sine wave. And it looks like the sine of an angle. If you vary continuously, it basically gives you angle if you vary from 0 to 360 plots like this. This is called a sine wave. The shape of a wave is called a sine. So this also is a sine. And y of x is also a sine. Y of t is also a sine. So you can actually write mathematically what it means. So what, instead of saying sine wave, we can actually write the mathematically what it means. So this, let us say this amplitude is taken as a, it's the t, and then we can write y of t is equal to a into sine omega t. This small w is called omega. What is the meaning of that? The meaning of that is when time changes, omega is just a constant. We are just multiplying some constant. When time changes, the value of y varies like a sine of an angle. That is called a sine. Similarly, we can also write y of x is equal to a into sine kx. K is simply a constant. So sine of k into x, it also varies like. So this is called a sine. So when you study more in trigonometry about how the sine function varies, you will get a better picture of this. So know this as basically displacement is nothing but a function of space and time. So you can actually combine both the equations and write here saying that y of x comma t means displacement as a function of both x and t is a sine kx plus or minus omega t plus y. So what does it mean? It means a is amplitude, sine is it varies as time, both with respect to time and space it varies as time, it varies as sine, and kx is basically telling us its variation with respect to space, and omega t is showing us its variation with respect to time, and plus or minus simply tells us the direction of the movement of the wave. In this case, wave is moving from left to right. Whenever wave moves from left to right, you will see a minus. Whenever that you will actually later understand by analysis. So when you have a plus here, that means wave is moving from right to left. Okay. And then the phi is nothing but we call a phase angle. That means from where it started. Did it start at a peak point or did it start at a point which is basically somewhere in between? So just to specify that, we will talk about phi, which you can at this point next. So it is basically a combination of space and time. That is what we want to understand. Displacement is a function of both space and time. So now, what about the sound wave? The sound wave, if you watch carefully, this is the sound wave is a longitudinal. Okay, in the sense that the particles of the medium vibrate like this, and the propagation also happens. So please take a look at that one small rectangle that I have, and watch inside that there is one single particle, maybe the red particle, which is just vibrating like not going in. So if you take that vibration, one of the particles, and actually plot it with respect to time, it will actually look like a small sine wave, and the peak of the sine wave is nothing but the peak of the wave displacement. Yeah, so that is how we can plot the displacement with respect to time. But there is one more thing that happens in a sound wave. In a sound wave, you can see very clearly. Let's say I am going to basically stop this, and when you stop this, you can see that in some area it is more compressed. Okay, we call this, let's say that take that area, it is slightly more compressed air, and we call that as a compression. And in some areas, it is actually slightly rarefied, means that very less particles are in there. We call that rarefaction. So compression, rarefaction. Okay, there are many such compressions and rarefactions. Compression and rarefaction progresses. The sound wave progresses like that. Okay, so now if I actually plot those compressions and rarefactions with respect to space, yeah, if you see this, wherever the higher compression is there the pressure is high. Wherever the compression is less, rarefaction pressure is less. So we call actually, let us say we can plot pressure versus x. You can see that compression point there is basically pointing to the peak of the pressure, and you can see the rarefaction point pointing to the least of the pressure. Yeah. So that is how you can plot. However, what you have to understand is that again we can actually plot like this and write a mathematical equation for that. It is basically P of x is equal to A into sine of kx, like that. So this is actually pressure. But now one more thing is possible. You can carefully watch actually the places where there is a compression. There the particles are vibrating with a lesser displacement. Where there is rarefaction, they are slightly higher. So it's actually inversely proportional. Displacement and pressure are inversely proportional. There you can see. So it's an inversion of that. So together here displacement we call it as f of x. So displacement in this direction is the inversion of our pressure. Now it is possible again here to write a displacement function as both x and t and call that as s of xt, which will be again sine of kx plus or minus omega t plus. So this both sound wave, which is a longitudinal wave, and the wave that we have shown on the beats, which is a transverse wave, both of them can be represented using a function like this, which is called as a wave function. A wave function is always a function of both space and time, that is x and t. So if we understand that much, then we can progress and learn more on waves. So we have completed basically oscillations, waves, wave basics. So when we get into hot topics, we can learn more about how to solve problems in oscillations and waves. Thank you.